Welcome to The Explainer. Today, we are diving deep into one of the most powerful tools in statistics, and we're going to do it by looking at one of the most heated public health debates of our time. We're going to see how cold, hard data helps us separate what's real from what we just fear. So let's start with a really high-stakes question, one that has fueled an incredible amount of concern and controversy for years. It's a question that absolutely demands a clear, evidence-based answer. This is the exact question a group of researchers wanted to answer back in 2002, and they had a massive amount of data to work with, from over 500,000 children. But all that data is useless without the right tool to make sense of it. We're going to use their findings to walk through exactly how that tool, the Pearson's chi-square test, actually works. So what is this thing? Well, you can think of the chi-square test as our go-to tool for this job. It's designed to look at two different things. In this case, whether a child was vaccinated or not, and whether they had an autism diagnosis, and help us figure out if those two things are actually connected, or if any pattern we see is just random coincidence. Now, here's where it gets really clever. The whole logic of this test is about comparing two different worlds. There's the world we actually see in the data, and then there's this hypothetical world where there's no connection between our variables at all. This right here is the aha moment of the test. It pits reality against a carefully calculated fantasy. On one side, you have the observed reality, the raw numbers from the real world. And on the other, you have the expected reality, what the numbers should look like if vaccination and autism were totally, completely unrelated. The size of the gap between these two worlds, well, that tells us everything we need to know. Okay, so first up, let's look at the observed table. This is the real deal. This is what the researchers actually found. You can see right there, for example, out of more than 440,000 vaccinated kids, 621 were diagnosed with autism. This is our ground truth. So, you might be wondering, how do we build that hypothetical expected world? It's not just a guess. We use the totals from our real data, the row and column totals, to mathematically figure out what each little box in the table would look like if there was absolutely no relationship. We're creating a baseline based on the idea of pure chance. And here's what that expected world looks like. Now, if you just glance at it, the numbers look pretty similar to the real data, right? But they are different. For instance, we observed 621 vaccinated children with autism, but in our no-link world, we would have expected to see about 605. The next step is to measure the total difference between these two tables. All right, let's move on to the next piece of the puzzle. We've got our two worlds, the real and the hypothetical. Now we need a way to boil down the difference between them into a single, meaningful number. And that single number is called the chi-square statistic. For every single box on our table, the test calculates the gap between what really happened and what our no-relationship hypothesis predicted. Then it adds all those little differences up into one final score. The bigger that score, the bigger the gap between reality and random chance. For this data, after all the math gets crunched, the chi-square statistic comes out to 2.28. This one number represents the total difference between what was actually observed in over 500,000 kids and what we'd expect to see if it was all just random. Okay, so we have this number, 2.28. But what does that even mean? Is that a big deal? Is that a large enough difference for us to sit up and say, hey, something's going on here? Or is it so small that it could have just happened by pure random luck? To answer that, we have to calculate something called a p-value. Now, the easiest way to think about a p-value is as a kind of surprise score. It tells us the exact probability of getting a result like ours, a chi-square of 2.28, or even higher, if the starting assumption of no relationship is actually true. And the p-value that comes out of our test is 0.1309. So what on earth does that tell us? It means there's a 13.1% chance that we'd see a difference this big just by random luck, even if there's no real connection at all. Now, in science, the standard cutoff is usually 5%. If the p-value is less than 5%, we say the result is statistically significant. Since our result, 13.1%, is way above that, our conclusion is clear. We just don't have enough evidence to claim there's a real link. But, like any powerful tool, you can't just use it whenever you want. The chi-square test has some important rules of engagement, some conditions that have to be met for the results to actually be trustworthy. So, for the test to work properly, a few things have to be true. The groups have to be independent, and crucially, the sample size needs to be big enough. And with data from over 500,000 kids, you better believe this study easily clears that bar, which just makes the conclusion that much stronger. And this is a huge one. This is so important to understand. Even if we had found a significant result, the test would only tell us that a connection likely exists. It wouldn't tell us if vaccines make autism more or less likely, or by how much. It's really just a smoke detector. It tells you if there might be a fire, not how big the fire is. Okay, so we've waded through the math, but this brings us to what might be the most important takeaway of all. It's not just about the numbers, it's about understanding the language of science, especially when it's up against the language of fear. Just look at the difference here. On one side, you have the alarmist claim. It's bold, it's certain, it's absolute. This causes that. But then look at the scientific statement. It sounds so much more cautious, doesn't it? But as we're about to see, that caution isn't a weakness. It's actually a sign of incredible intellectual rigor. This careful phrasing isn't a sign of weakness, it's a mark of honesty. Science works by trying to find evidence against an idea. Proving a negative, proving something absolutely 100% does not exist is pretty much impossible. So this careful language isn't wishy-washy. It's the very hallmark of scientific integrity. And it's so important to remember where this specific fear even came from. It all traces back to a single, fraudulent paper published back in 1998. The study was later found to have completely manipulated its data. The journal that published it retracted it, and its author actually lost his medical license over it. And that right there is the real beauty of a tool like the chi-square test. It gives us a tough, mathematical way to get past scary stories and gut feelings. It lets us check if a pattern we think we see is a real, meaningful signal or if it's just random noise. So in the end, this isn't just a math lesson. It's about learning to hear the difference between a loud, confident claim and a quiet, careful conclusion. It's about learning how to find the real signal in a world that is full of noise. Thanks for joining us for this explainer.